Welcome everyone. In this video I'm going to continue the work with the AS5600 magnetic position sensor. In my previous video I have already built a system which has this board, and this is this system. You can see it here. It's a PCB mounted on the bottom of a NEMA 17 type of stepper motor, and that PCB is this guy here. Nice blue PCB, as you can see. And the PCB has the AS5600 chip in the center of it, and then this chip faces a magnet, a specially magnetized magnet, which is attached to the shaft of this stepper motor. And as the shaft rotates here, the magnet also rotates with it because they are attached together. And then the magnetic sensor, which has 4 Hall sensors in it, will be able to determine the position of the shaft, and by using some careful coding we can detect the changes and also follow the changes of this displacement, and we can determine the position and the speed of the stepper motor. And I built up a system with a few extra components as compared to the previous video. So for example, I added a stepper motor driver. And what I will do here is I will demonstrate how this board works when we want to measure the position and we want to measure the speed. So I will drive the stepper motor with this Arduino. I will show the position on this OLED display, and we will see how the software created speed and position, so the values calculated by the AccelStepper library, differ from the position and speed which we measure by the magnetic sensor. And I also want to solder another board, so I prepared some soldering equipment and parts here, because I figured out a better arrangement for my microscope camera, so I can probably record the wall surface in the same field of view, and that would result in a very nice video, hopefully. But before soldering this PCB, I would like to tell you that this video was sponsored by the maker of this PCB, PCBWay. So PCBWay is a PCB manufacturer, mainly focusing on PCB related services, which means that they can also assemble the PCBs for you, and they can make much more advanced PCBs as well as compared to the one which I show you in this video. So if you use their services, you can get the full service that is needed to get the wall circuit done. So you will receive a circuit which is ready to be used. But other than these PCB related services, they can also offer 3D printing, CNC machining, and other nice services. For example, if you have a custom enclosure, you can use their sheet metal fabrication services in order to make your custom enclosure. Or if you have some kind of very unique and special part, you can use either 3D printing for metals or polymers, or you can use CNC machining, and all these services are provided by PCBWay. And the order process is very simple. You just go to PCB Instant Quote, then you select Quick Order PCB, and after adding your Gerber file, you will be able to customize your board. For example, you can select the material of the board, or you can select the color of the solder mask, and so on and so on. And other than this, you can order an SMD stencil, which can be very useful if you have a lot of SMD parts on your PCB. Or if you want to skip the wall struggle, you can order their assembly service, which means that they will assemble the PCB for you, and you will receive a circuit which is ready to be used. And now during the Christmas period, PCBWay has its big sales. So they offer a lot of free Christmas coupons, special offers for PCB making and PCB related services. They offer a lucky draw, so you just register on their website, log in, and you have a chance to win even a robot dog. And you can further benefit by inviting your friends to PCBWay. So I hope you will like and use their services, especially during this Christmas campaign, because they have very nice discounts and very nice offers. So now we can proceed to the video, and I will tell you what will happen to this wall system. So I will change to another camera, which will focus on the surface of this PCB. And then I will put some low melting point solder paste on the tabs. And then the components will take their places. And finally, I will fire up this tiny reflow station and solder the things. So I finished with the soldering process, which was more or less successful. I had a little bit of short, but I could correct it with another resoldering. There was a bit of an excess material between C1 and C2, and I had to remove a little bit of solder blob. But otherwise, the rest of the things look fine. It's a bit ugly, but I can clean it and it will be very nice. So this board will be used in the future. But now let's go to this part and let's focus on this stepper motor thingy. And before proceeding, I would like to set up another camera similarly to the other video that I had recently for the PID control of DC motors. Check that in the top right corner. So I will record the screen with another camera, so you will see what is happening, and it will be easier for me as well to explain everything. So let me set up the camera and then we will focus on the stepper motor and its movements. So now the whole system is ready for demonstration. So you can see the assembled stepper motor system, and at the bottom we have the other board which I assembled. So we have the magnetic encoder in the bottom. And what we do here is that with this rotary encoder, I can change the speed by 10 steps per second increments in both directions, positive or negative, doesn't matter. And with that, we will speed up the stepper motor to certain speeds. And as you can see, I put an arrow, I printed an arrow shape. I put it on the shaft, so you will see the movement of the shaft more easily. And we will see it also in the video, how one full rotation looks like, and so on and so on. So on the display you can see total zeros for everything, and these are actually similar values in the two columns. So one column, the left hand side column, will show us the values obtained by the AccelStepper library. So the first value will be the speed in steps per second, and that's the speed that we determine, but all the other values are either calculated from this speed, for example, the speed expressed in RPM values, or provided by the AccelStepper library, for example, the position. And from the position, so how many steps we are away from the original starting position, we also calculate the angular displacement of the shaft. And this is a good comparison because actually we almost directly measured this with the AS5600 sensor. And that data will be shown on the right hand side or second column under the SCK-SDA letters on the display. You can see that. And so the second column is the same values. The first cell or the first line is showing the data in steps per second. So this will be the speed calculated from the angular displacement or the rate of the angular displacement, and we express it in steps per second because we know the microstepping. That's a very important parameter that we have to know, and in this case it will be 800 steps per revolution. So one full 360 degrees rotation on the shaft of the stepper motor will take 800 steps. So the stepper motor will do 800 steps to do one full turn. And this has to be used to be able to translate the rate of the angular displacement into steps per second. And then we have the RPM. That's almost like a raw data that we can read. We know the time interval that we use to check the displacement on the shaft, and we use this to sort of extrapolate to RPM. And then we have the position in steps. This is also calculated from the total angular displacement measured by the magnetic encoder. And finally we have the total angular displacement, which is almost like a raw data that we can obtain. So since everything is set up, I slowly start moving the motor. And one thing that I have to tell you here is that I was a bit lazy and did not match the signs of everything. So while the motor is moving counterclockwise, the values will be positive. So don't be surprised that by common sense we should get negative numbers, but now I have to tell you that my, let's say, coordinate system is flipped. So when the motor will move counterclockwise, it will produce positive numbers, and the other way around. So when it moves clockwise, it produces negative numbers. So I start increasing the speed, and you will see the values on the display of the Arduino. So as you can see, we have 10 steps per second speed, which is equivalent to 0.8 RPM. And you can see the number of steps done in the third line. And in the fourth line, you can see the angles stepped. So now we are more than 100 degrees, 110, 120, and so on and so on. And you can see that this works very nicely. I speed this up a little bit just to complete one full rotation, and then you will see how precise the two things are. So I want to reach 360 or 800 steps. So now the speed is 0, as you can see, and I stopped at 800 steps. And as you can see on the left-hand side column, that is the data produced by the AccelStepper library. So that is just basically the numbers which are controlling the so-called open loop system. And you can see 800 steps, 360 degrees based on the mathematics. That's just pure formula. And on the right-hand side, we have the measured values provided by this nice little board here. And that's very cool because they are identical. Of course, there is a tiny jump at the end in the second digit of the degrees, but that is just digital noise, in fact, because the resolution of this sensor is 0.088 degrees, roughly 360 degrees divided by 4096, and that's what you see there, digital noise. So it's yeah, plus minus 1 bit, basically, what we see there. And all the others are similar parameters. So what I do now, I will just speed up this motor to 60 RPM, which means that we do 800 steps or one full turn per second. And you will see how this system behaves. So now we are at the theoretical 800 steps per second. And you can see that that is 60 RPM. And this is these values are just calculated by the fact that we have 800 steps per revolution microstepping, and the rest is just pure, simple mathematics. And you can see the two bottom lines, they are basically identical, and the only thing which is different is the speed a little bit. And this is just probably due to my poor programming. When we go to the code, we will see if I messed up something or not. But I have noticed that the speed is not always correctly followed by the magnetic encoder. And I tried some parameters, but I still haven't succeeded with this. But now if I go back to 0 speed, we can check how the other two numbers are aligned. So I slow down the motor to 0. It should stop. And we can see the two numbers, and they are pretty much identical again. So you can see that we moved randomly so much steps, in fact 56,000 steps, and still the AccelStepper library with the open loop system is the same with the measured values. So I measured the values with the magnetic encoder, and they are just the same. And you can see that if I start to move in the negative direction, actually I will decrease these numbers in the bottom two lines, which means that these two lines are also on an absolute scale. So it's not like a relative scale in this sense, that if I start to move again, it is this position which is the new 0 position. No, the 0 position is the position where we started up the whole system. So now I move in the other direction. And you can see that we have negative numbers, and we are actually going towards 0 now, so we are decreasing the values, and we can go very fast as well. So this is 120 RPM, and you can see that the numbers are going down very nicely, and you can see that there is a slight difference between the two speed values. So the theoretical speed is for some reason not the same as the measured one, and I still have to figure out why, but you can see that this works very nicely. And this can be further programmed, and I will do that into a closed loop control. I will try to stop at 0. It's not too easy when you try to look at the monitor of the camera and try to see how the numbers are aligned. But as you can see, without any kind of manipulation, I could go back to 0. So the AccelStepper library actually did not skip any steps. And this is kind of an important lesson, because if you don't overload your stepper motor, you don't need a closed loop control for your stepper motor, because it will move the same steps as you command. So it's pretty nice that if you have a nice system set up with the stepper motor, then you can sort of rely on the stepper motor and you can trust the position. But of course, sometimes it's good to have good information about the position. So this circuit still has its own, let's say, justified position in these kind of projects, because you can actually control and check the number of steps with an external hardware. So it's always good to have a confirmation that the stepper motor really did those amounts of steps that you asked for. So yeah, as you can see, this system works very nicely, and you could see my clumsy soldering as well. So it's quite successful now. And then now the next step is that I will show you the software, because now I extended my original AS5600 software. So now we have all these functions which make possible that we can provide the numbers on the display. And I'm going to show you those parts. So let's go to my computer and let's go through the code and see how it works. Alright, so let's see what this code is capable of. And I'm not going to explain everything very carefully, because I have my original video on this magnetic encoder. Therefore, I will only focus on those parts more which are new in this code. So first of all, please check my video where I explain like every part of the code for this kind of board. So here, the first thing which is very important is I'm using this timer library, which is basically using the physical timer of the Arduino, and in this case I'm using the timer 1 to do some interrupt-based tasks. And here I will do it because I will move the stepper motor within an interrupt in order to not skip any steps and give a priority for stepping the motor. And then naturally we have to have these libraries for the OLED, and we have to have this kind of configuration stuff. And if you want to use STM32, keep in mind that the SDA and SCL pins are at these two pins, PB7, PB6. And since we are using a stepper motor, we need the AccelStepper library, and this does nothing else than we just have this stepper instance, and the steps are provided by the pin number 10, and the pulses are provided by the pin number 11 on the Arduino Nano. So these go to the breakout board. And here we have the stepper motor speed variable, which is simply a volatile float, because this is the parameter that we change with the rotary encoder. So it has to be volatile because it's changed in an interrupt. Then these are nothing fancy, just the typical things for the rotary encoder. So I'm not going to explain these. And then also these things are, most of them can be found in my video, but what I have here are more like these things. We have to have a variable for the RPM value because that is needed to be stored somewhere. And then we have a step rate, so steps per second calculated from the RPM value. So this is a good thing because then we can calculate the difference or display the difference between the steps per second set up by the AccelStepper library or by the user, us, and the steps per second speed calculated from the RPM value, which is the measured value based on the displacement of the shaft. And then this is calculated based on the steps per second given by the AccelStepper library. So we store that as well. We have the position of the stepper, again, an AccelStepper library based data. And then I store the previous position as well because this parameter is used to update the display. So that's what we have. And then this RPM interval is not correct. Now it's good, the comment. So what this does is that it looks at the angular displacement or the displacement of the angular displacement, basically. So how much degrees we moved since this previous checking. So we check this every 200 milliseconds and we calculate or extrapolate the RPM based on this. Maybe it's not too good for very slow speeds, but for fast speeds it can work well because we have significant amount of displacement within this very short time. You can play around with this. And then RPM timer is just the timer for the RPM value measurement, so nothing else. Then we arrive to the setup and we have this timer. So we initialize the timer 1 and we initialize it with a 100 microsecond trigger interval. And here you have to be careful with this interval because it has to be much quicker, or quicker at least, than the interval which you expect to have as the maximum interval for updating your stepper motor. So you have to match this value with the speed of the stepper motor, and you can calculate it very easily, so you know the frequency basically, and based on that you can calculate the inverse of it, and you know that, okay, if you have let's say 60 RPM, then this and this values will be the frequency of the stepping. And yeah, so for example 60 RPM is 800 steps per second in our example, and that means that 1/800 seconds will be the frequency. Then we initialize or we start the serial port. I'm not using it when the code is running, but I used it for debugging because I can send all these informations to my computer, which makes everything much easier. And then, of course, we have the I2C, and then we have to check the magnet's presence. So if you haven't assembled your board properly, the code will get stuck at this line, and it will not move anywhere. So you will not see anything on the display, you will not get anything, because this part basically blocks the whole Arduino code until you manage to find the correct position for the magnet. And then we read immediately a position, and that will be our starting angle, because this is an absolute encoder. So when you start up the Arduino and you have the magnet aligned in any kind of random way, you will read out any random angle between 0 and 360. So then, for example, you measure 183 degrees, then that will be your starting angle, but that has to be subtracted from the subsequent readings, because otherwise you don't get a nice zero position. So this is why I did this. And then this is also copy-paste, just the Adafruit library for the OLED display. And then this is also copy-paste, just the pins for the rotary encoder. So CRK and DT, these are the two rotary encoder pins, and SW is for the switch on the rotary encoder. And then We need an interrupt for this, so we are using one of the interrupts here, and whenever you rotate the rotary encoder, it will fire the function which I called rotary encoder, and we will do something in that. In this specific example, we will increase or decrease the speed. And then we just read the 2 pins, so we have like references up on the next rotation of the rotary encoder. This is also copy-paste. I just print something out to the display, wait a second, and then I clear the display and refresh it with the parts which I want to print on the display. And then this is very important. This is the setup for the AccelStepper library. So in the beginning, the speed has to be set to 0, so we don't run. And then the max speed has to be defined anything which you expect to be your maximum speed. But what we will change within this exercise will be the set speed function. And acceleration, here it's not really significant because we don't apply any kind of acceleration. So it's fine to be anything, but you can give any kind of large values to it. So then we have this callback function, and then this callback function is basically triggered by the timer. So here we have this attach interrupt callback. So whenever 100 microseconds is elapsed, the Arduino throws away everything basically and comes to this function and tries to do a step if there is a time to do a step. So this is what we do here. And then the loop, I put everything in functions, try to arrange everything neatly. What we have here, first we read the raw angle, and that's the absolute encoder value basically. And then we correct the angle, so we tear it and then we do everything. We check the quadrant, so we check how the magnet was rotating. And then we do the calculations based on the magnetic encoder and the AccelStepper library. And then we are polling the button if it was pushed or not. And then we throw everything on the display. And you have to be careful because this can be time consuming, so you always have to check the timings. For me, it's about 40 to 50 milliseconds. And that might interfere with certain things, so you have to be careful with this. And here, in every iteration of the loop, we reset the stepper motor speed to the most recent value, which was set by the rotary encoder. So then one thing which I will not talk about is this read raw angle, because this is already explained in my previous video. Please go there and check it. I also put the link in the description, so it will be easier for you to reach it. But basically, we have an I2C communication with the AS5600, and we just request the angle, and then we reconstruct the numbers because they come in as 2 8-bit numbers. And that's all. And the correct angle, I will also not explain it because I explained it in the other video. Check quadrant also. Check magnet presence also explained, so I skip over this. And now comes a part which will take a bit more time. So here we calculate the RPM value based on the elapsed time. This is what I tried to explain previously. And the change in the total angle. So what we do here is first we calculate a difference. And what we do here is that we check the current time, and basically this is the previous time. So we do that. And if the time difference is larger than the interval, 200 milliseconds in this example, then we enter to this part. And what we have here, this line which I commented, strictly depending on the 200 milliseconds, and that might not be good because sometimes the timers are not too precise. Sometimes this condition can be fulfilled when this if condition checks the timer when not 200 but let's say 210 milliseconds elapsed, or 250 milliseconds or whatever. So it's much better to actually rely on the real elapsed time. So what I do here, I divide 1 minute with the timer difference, and then I multiply it by the change in the angles, and I divide it by 360. And then I get the RPM speed. And here I explained everything, so I'm not going to do more. Now I jump to the step rate for RPM. So this is the speed defined in steps per second, and this value is compatible with the value which is used by the AccelStepper library. And here is the very important moment that we have to keep in mind. We have to know the microstepping that we are using. And here I define that we are using 800 steps per revolution, and that's very important. So we have the RPM value, and that has to be multiplied by the microstepping and has to be divided by 60. And this will give us the exact number. Why? Because the RPM value, let's say that is 60. So we have 60 turns of the shaft per minute. So then if we divide it by 60, we know the number of turns by a second. So that is 1 in this case. And we know that we have 800 steps per revolution microstepping. So we multiply this 1 by 800. So we get the steps now 800 steps per second. And that's correct. Then we just update the values. So we will know the difference again when we enter this part. And we also update the timer. So that's all basically in this part. And then we have the refresh display. So now this is basically the alignment. First column, these numbers here. These are the AccelStepper library based numbers. Maybe it makes more sense if I separate them. So steps per second and position, these are provided by the AccelStepper library. And then what the AS5600 does is that it provides us the RPM and total angle. And then all the others are calculated. So you see that here we have RPM as raw data from the magnetic sensor. And here we calculate it from the steps per second. And for example, here we don't have the AS5600 provided speed in steps per second. Instead of that, we calculate it from the RPM, and so on and so on. And I'm not really going to explain this because it's very simple. We just have a refresh rate, but other than that, we check this set of conditions. If there is a change in the position or something like that, then we allow the display to be updated. So if the magnetic encoder is not moved and the rotary encoder is not moved, these are not performed. And I explained here everything line by line very nicely, I think. So this is, for example, one line. This is the first column, and this is the second column. You can see the shift in the X. And this is how it works. So this doesn't need any explanation. So this is all. And then what the rotary encoder does is very simple. We check if some rotation was done. And then we check what was the direction of the rotation. And based on that, we do something. For example, here, I decrease the stepper motor speed by 10. And I also recalculate the RPM based on this value. And here I also change the stepper motor speed by 10, but in the positive direction, and I recalculate the speed. What I can do here actually is this, because it's enough to have it in one line. It doesn't do any special stuff, but it looks a bit more clean. And what the button does, it just resets everything. I haven't shown that in the video, but it's nothing else. It just puts the numbers to 0. It's like when you reset the Arduino almost. So we check, we read the rotary button value, and if it was 0, this depends on how you wire your button, pull up or pull down resistor, and so on and so on. So if that was done, and the last button press happened more than 1 second ago, then we just allow the software to put everything to 0. And then basically this kind of, I don't know if we can call it algorithm, but this kind of technique is sort of a debouncing. So if you press the button too often, nothing will happen, because the code requires to have more than 1 second elapsed in order to perform anything which is inside these brackets. So it's kind of a cheap way to do debouncing on buttons. So then basically this was all. It's nothing too extraordinary, and I think I explained all the formulas properly also in the comments, so you will see how the certain things are performed and how you can calculate them yourself. So for example, if you change the microstepping, you can replace the numbers and you can have it in your way. And basically that's all. So I hope this video was useful to you, and I hope you can use this for your own projects to, for example, follow the steps of a stepper motor or control it based on the information that you get from the magnetic encoder. Please check my website, because I have all the resources there. This source code is uploaded there, and I have the drawings and maybe some nice pictures, and also you can find the parts I used there. And also don't forget to visit PCBWay.com, because they have very nice services, and you can make this same PCB that I made by using my links. So check the description, check PCBWay.com. I hope you learned something. I hope that this video was useful, and see you in the next video.